Hello students, welcome to the Cryptography and Network Security Module 2. In the next session now we are going to learn about the elliptic curve cryptography. So in this we are going to first see elliptic curve Diffie-Hellman key exchange. So how elliptic curve cryptography provides security by using the asymmetric cryptography. So before that we need to understand how the key exchange takes place. As you have already learnt about the Diffie-Hellman key exchange, the elliptic curve also makes use of the Diffie-Hellman to exchange the keys. Now let us try to understand elliptic curve first. See, this elliptic curve cryptography, it is actually an alternate technique to the RSA algorithm, right? So we have seen RSA algorithm, right? So as we know in RSA algorithm, uh, the security lies on in the factoring of n, correct? So how hard it is to factor n, that is where the security of RSA lies. Now what we can say is this elliptic cryptography, it provides security equal as RSA, but by using even a lesser key size than what RSA was using. See, to tell you, if I have 256-bit key size with respect to ECC, that is electrical cryptography, it provides security provided by RSA by making use of about 3048-bit or so. Right, so that much difference we have with respect to ECC and RSA. Now here, the ECC approach primarily depends upon the mathematics of the elliptic curves. So when I say elliptic curve, so you can observe here, we have taken one elliptic curve which satisfies the equation y is equals to x cube plus ax plus b. Right now, so you don't worry about how this curve is drawn, but just let us try to understand its characteristics. Right. So now this curve, which you can see that it is symmetric on both sides, right, and it extends infinitely again at the both ends. It extends infinitely at the both ends, but we are restricting ourselves to the point n. Right, let us say consider this is our finite field, right? So it is actually an infinite field, but we are trying to restrict ourselves into a finite field. Now, at any point in time, if I draw a line by considering the different points on the curve, at any point in time when I draw the line by considering different points on this particular curve, there will be only 3 points, maximum of 3 points we might get. Right. So suppose consider now you have a line, as you can see a blue color line here. You have point P, Q, and R. There is 3 points is there. Suppose consider I draw one more line like this, right? So if I draw one more line like this, now you can observe that it is cut at only 2 points on the curve, right? So that is what I said. Maximum it can cut at only 3 points. It can even cut at 1 point, it can cut at 2 point and 3 points maximum. Fine. And when it is symmetric, that is point on either side is symmetry. Okay. So that is the characteristics of this elliptic curve. Right. Now let us try to understand what the elliptic curve Diffie-Hellman key exchange is. It basically involves 5 steps. Right. The first step is to select the domain parameter. Second step is generating the key pair. Third step is exchanging the public keys, computing the shared secret, and deriving the symmetric key. See, this is almost equivalent to what we have seen in DES, right? Sorry, Diffie-Hellman key exchange, right? Yes. So let's see what is that each step has. Right. In step one, we are trying to select the domain parameter. So this is your public parameter, right? Even we in case of Diffie-Hellman we had public parameters, right? Q and alpha, the prime number and its primitive root, right? Yes. So here what we are having is, here we are having an electric curve with the parameters A, B and Q, where Q is a prime number, or it can be any number of the form 2 power m. Right. So this is the curve that we have considered. So as you can see in the previous case, the example curve that we had taken, it was like, say, y square is equals to x cube plus ax plus b, right? So this was the curve that we had taken. So here, something like that, this curve is also, this eq of a comma b represents the same. And we are considering on point G, this point is on the curve and whose order is as large as value n. So as I told, in that curve, we are restricting ourselves to a finite field, right? So where we are restricting it to n. So that n is what is this? Okay, fine. So this is about the selecting domain parameters. You have electric curve with the parameters a, b, and q. Here q is a prime number, or it can be a number which is of the form 2 power m, which can be represented as 2 power m. And g is a point on the curve whose value can be as large as n, not beyond that. Right now, so we are going to generate key pairs. So when I tell we are generating key pairs, so key pairs, that is public key cryptography, we are making use of. We want private key as well as we want public key, right? So as you know, private key remains private to the user, and public key will be shared in the public domain. Now, what user A does is, user A selects a private key NA whose size which is less than n. Right, as I told, if suppose consider I want 256 bit key size to be used, so n can be 256 here, something like that. Right, and it will calculate its public key PA. How is it calculating? It is calculating. It's the point multiplication that we are having. Right, so we are having point multiplication on the curve. Right, this point multiplication, it has several properties. It is commutative in nature, associative in nature. It follows closure property. Right, so we have certain properties for this particular G. So just to perform the point multiplication. So it's like telling that the point on G is added n a number of times. So that is how it is. Point multiplication is nothing but you have G and you are adding it n a number of times. So that is what is point multiplication gives us. Similarly, at the user B side, if I consider the user B takes NB as the private key and its value should be less than n, it is going to compute its public key PB, which is again NB into G. So this again is also a point multiplication. So that is how key pairs is generated. Public key and private key. NA, NB, private key of A, private key of B. So using that, multiplying it with the point G on the curve, so we are going to get the public key. Right. So this is the key generation. And next is exchange of the public key and computing the shared secret. Now in this step, what happens? The public key that is created, right? So PA that is generated or created, PAPB. So B will send PB to A, and A will send PA to B. So this is what we also see in Diffie Hellman, right? Yes. Now using this, a shared secret will be calculated. Key K will be calculated by multiplying NA into PB and K NB into PA. So this is the same as in the previous case of Diffie-Hellman. So shared secret or secret key is generated, calculated. Now, see, this key, it is calculated by the respective entities only. Right? It is not shared over the channel. Only thing that is shared is the public key PA and PB, which is shared over the insecure channel. Now, if you consider that key, now considering NA has generated this key, so NA uses, I mean A has generated the key, so A uses its private key NA and multiplies it with the public key of B. Now, So let us try to derive this like how we did in Diffie. Now this is NA. What is PB? PB is nothing but private key of B multiplied by that point G, correct? Yes. As I told, point multiplication is commutative in nature. I can, as well as it is associative, as well as it is it satisfy closure property. This I can write it as NB into NA multiplied by G. So when I write this, NB into NA multiplied G will give me public key of A. Now private key of B, public key of A will give me the K. So as you can see, I have derived the symmetric key. So with this, what happened? The key exchange took place by using the elliptic curve. So that is why the name elliptic curve Diffie-Hellman, same as what we did in Diffie-Hellman, but only thing is there we had only two parameters q and its primitive root. Here we are considering the generator g on the elliptic curve, which is a point on the elliptic curve, and we are making use of one elliptic curve. So that is how key exchange is achieved. Thank you, students.